So 6.6, we are going to focus on just the sine and cosine functions. So don't worry about tan and all the reciprocal functions, just these two. So I've got a couple of resources here. This first YouTube video I think it's great. It's sort of focusing on the uses of the trig functions, which I might show even in one of these videos, but maybe when we do applications. And then this one, which just allows you to play with A, B, C, and D and just sort of see what it does to the function. But I do recommend watching this first one. I just think it's great. It's got great jazzy music, just so you know. And it might inspire you to be like, oh my gosh, I can use trig in so many ways. And in fact, one of the journal topics is finding an application of a sinusoidal function in a field you're interested in, maybe medicine or science or electrical or engineering, and writing about it. So find some sinusoidal wave within that and then talk about how it's used, or maybe some of the terminology that you're going to learn in 6.5 and 6.6 and how it applies in that field. But what we are going to do is we are going to graph transformations of sine and the cosine functions. So I've written both functions in this form. Y equals a times sine of b times x minus c plus d. And same thing with cos. Y equals a times the cos of b times x minus c plus d. And what I want you to be thinking of is functions. Y equals a times f at b of x minus c plus d. And it's the exact same thing. So see if you can pull from the recesses of your brain. We've done tons of transformations throughout most of the chapters in this semester. What can the A do? Right? What sort of transformations is A responsible for? Well, the first thing I want you to know is it's a transformation on Y, right? So what's the other transformation on Y? That would be D, okay? And A can do two things. It can reflect the Y values over the x-axis, and it can also vertically stretch or shrink your graph. And what we're going to be looking at is what that does to a sinusoidal function. And then the next transformation is B. What does B do? Well, it's a transformation on x, so hopefully you're thinking, opposite as it appears. It can also reflect. Now it reflects the x values over the y-axis. And it can also horizontally stretch and compress, or stretch and shrink your graph. And then we're going to look at, again, what will that affect on a sinusoidal graph? And then C is also a transformation on x. It can move it left and right. And then D is a transformation on y, and it can move it up and down. So it doesn't matter whether you're talking about sine or cosine, the A, B, C, D is going to do the same thing. So technically, you already know 6.6. You know how to transform a graph, and we're just going to transform a sinusoidal graph in particular. So we're going to work through these alphabetically. So I'm going to do the transformations A, B, C, D in order. So the first transformation we're going to look at is the transformation A. And we're going to look at the vertical stretching and shrinking, and as well a little bit about the reflection of the graph. So the first thing I've done is I've got three graphs drawn over here. I've got y equals cos x, which is the gray graph. I've got y equals 1.5 cos x, which is the green graph, and y equals -2 cos x, which is the giant pink graph. Now I know you guys don't have colors on your sheets, and I also do think it gets kind of confusing trying to look at it there. So what I'm going to do is I'm going to graph them here. I've got y equals cos x. So this is my y equals cos x graph. So let's look at this one first. And let's talk about the different features of this graph. So what do we know about cos x? Well, we know that it has a period of 2 pi. Why do we know that? Well, we know that one full rotation is from peak to peak. So if I look at this cos x graph, you'd go from 0, and it's just right on the edge here at 2 pi, so from peak to peak. Or you could go from trough to trough, it doesn't matter, or midline to midline, right? Regardless, it's a distance of 2 pi. Amplitude is 1, right? Amplitude being the distance from the center line up to the max or the min. The domain is -infinity to infinity. And the range is -1 to 1. Okay. The next graph I want to look at is y equals 1.5 cos x. So we're going to go y equals 1.5 cos x. Whoa, sorry. What did it do? 1.5 cos. Okay, y equals 1.5 cos x is the blue graph. How does the blue graph compare to the red graph? Well, hopefully you know that 1.5 is greater than 1, so I'm getting a vertical stretch. And so what's changing? Well, does the period change? Nope, it still has peak to peak of a distance of 2 pi. Does the amplitude change? So the midline is still y equals 0, but now it's going up a distance of 1.5. So the amplitude is 1.5. Did the domain change? Nope, still negative infinity to infinity. And did the range change? Well, my top of my graph is at positive 1.5. The bottom of my graph, or min, is negative 1.5. So yes, my range is negative 1.5 to 1.5. Okay, what about y equals negative 2 cos x? So I'm going to get rid of the y equals 1.5 cos x. And the first thing I'm going to graph is y equals 2 cos x. I know this isn't the one that's written, and I'm going to do that on purpose, so I'm just going to maximize this guy. So if we first off look at y equals 2 cos x, what changes? Well, the amplitude, right, and the range. The domain doesn't change, the period doesn't change, but it goes up to 2 and down to negative 2. So that's one difference. What if I put in the negative? So I'm going to graph y equals negative 2 cos x. This is now the purple graph. How does the purple graph compare? Well, compared to the green graph, it's just reflected in the y values over the x-axis. For the red graph to the purple graph, it's a vertical stretch and a reflection. Property-wise, if we look at it, okay, what is the period of my purple graph? Well, it's still 2 pi. What is the amplitude? Well, it goes up to 2 and down to negative 2, so the amplitude is 2. The domain is still negative infinity to infinity. That's not getting affected. And the range is now negative 2 to 2. Oh, sorry, that came out really wrong. Negative 2 to 2. So now let's talk about A in general. So for A in general, what did A determine? Well, A determined the size of your amplitude. It determined how high or how low you're going to go. The amplitude is actually the absolute value of A. So A being the number written in front of your sinusoidal function, the amplitude is the absolute value of whatever number is written there. When A was greater than 0, we got a vertical stretch. When A is between 0 and 1, I didn't show any of these, so here, let's just quickly do one. So if I quickly did y equals, let's just do 1/2 cos x. 1/2 cos x. How does the green graph compare to the red graph? Well, it goes up half as high. So that's your vertical shrink. So if your A value is between 0 and 1, you get a vertical shrink. Ooh. Sorry, my pen is really carrying there. And then if A is less than 0, so if it's negative, you get a reflection of the the y values over x-axis. Okay, so now what we're going to do is just look at the sine graph. So y equals a sine x. So I'm not going to graph these, but I'm just going to say if I give you, or sorry, it says what about the amplitude of y equals a sine x? That's what I meant. It's still the absolute value of A. Sine and cosine, same thing. Now what I want you to do is determine the amplitude given an equation. So if I give you y equals 3 cos x, without seeing a graph, could you tell me what the amplitude will be? Well, it's always the absolute value of A. A is 3, so the amplitude is 3. If you have a graph y equals negative 5 sine x, again, it's the absolute value of that negative 5. So then the amplitude would be just 5. If you have y equals 1/2 sine x, then your amplitude is 1/2. So it's just the absolute value of whatever number is written in front. And the key thing for graphing is it tells you how high or how low to go. And if it's negative, instead of starting by going up, you just start by going down. All right, so which of the following characteristics will a vertical stretch or compression, stretch or shrink, affect? Does it affect your amplitude? Heck yes, it is the absolute value of A. Did it affect your period? Nope. Did it affect your domain? Nope. Did it affect your range? In fact, your range, your y values, are going to be between your min and your max. And so oftentimes, until we have a D transformation, it's going to be from negative A up to, actually we should do this in interval notation, shouldn't we? So in interval notation, it's going to go from negative a up to positive a. And then we'll change that when we put in our vertical shift. Does it affect your x-intercepts? Nope, because their y values are 0. And does it affect your center line? Nope. So it affected your amplitude and it affected your range. Now let's practice graphing. So graphing is something I do a little bit differently for sinusoidal functions than I did when we were talking about, transformations in general. Because sinusoidal functions are very cyclical, they happen at very regular intervals and do a very predictable pattern, we just kind of have to figure out where that pattern is going to happen. So I'm going to show you through this what's going to happen. Now looking at this, the first thing I'm going to notice is that there's two transformations. The first one is it's going to be reflected over the x-axis. And secondly, it's going to be a vertical stretch by 3. Okay, so without graphing, can we answer all of these questions? So the first question is scale. I just want to know, can you look at a grid and determine what the scale is? So it's going to take 4 grid lines to get to pi, which makes the scale, so each individual grid line, worth pi by 4. So my scale is pi by 4. The amplitude is going to be the absolute value of a, so the amplitude of this graph is going to be 3. The period isn't affected, so it's going to be just 2 pi. Now there's this thing called key points. So first off, I'm going to graph a basic sine curve. So I'm not going to do the transformation yet. I'm just going to say, what does a basic sine curve look like? Well, a basic sine curve starts at 0, 0, and then at pi by 2, which is 2 grid lines, halfway to pi, we go up to 1, and then we go back down to 0, down to 1, negative 1, back up to 0. And it would do that on the other side as well. So this is your regular sine x graph. For your regular sine x graph that has a period of 2 pi, how many key points did I draw between 0 and 2 pi? Well, there's 1, there's 2, there's 3, and there's 4, because this one's just the start of the cycle again. So if you're talking about key points, in the distance from 0 to 2 pi, we had 4 key points, which means that everything happened at pi by 2, which we know anyway, because if you think about building the sine graph, right, you've got this point 1, 0, you've got a point 0, 1, you've got a point negative 1, 0, and you've got a point 0, negative 1. We know that sine follows y, so it went 0, 1, 0, negative 1, back to 0, and it does this at your quadrantal angles, pi by 2, pi, 3 pi by 2, and 2 pi. So we can look at this graph and say, okay, well, if the period is 2 pi, then my key points are going to happen every pi by 2. And then it's good to look at your graph and say, well, what distance is pi by 2? Like if I want a key point every pi by 2, how many grid lines did I go? Oh, I went 2 grid lines. So my key points are going to happen every 2 grid lines. Another way of figuring that out is that if your key points have to happen every pi by 2 and your scale is pi by 4, you can do pi by 2 divided by pi by 4, which is pi by 2 times 4 over pi, which simplifies to just 2 grid lines, right? So that's another way of figuring out how many grid lines you want your key points to be. The domain of this graph is going to be negative infinity to infinity, because the domain of every sinusoidal function, that's not a reciprocal or tan. So sine and cosine are all negative infinity to infinity. And the range of this graph. So we said that range goes from negative a to positive a. So it's going to go from negative 3 up to positive 3. So now sketching this, where do I start a sine graph? Well, I start a sine graph at 0, 0. That's not going to get affected by a transformation of a. Then in 2 grid lines, I'm going to go up to 3. So I'm vertically stretching all of this original function by 3. Then at pi, so another 2 grid lines, I'm going to go back to 0. Then I'm going to stretch this point at negative 1 down to negative 3, and then come back up to 0. And then I'll repeat this cycle the other way. So in 2 grid lines, I go down to negative 3, back up to 0, up to positive 3, and down to 0. Now, that would graph y equals 3 sine x. If I want to make it negative 3 sine x, I should have done that in another color, sorry. If I want to make it negative 3 sine x, the only difference is that instead of starting by going up, I start by going down. I'm going to reflect all those points over the x-axis. So I'm going to start here at 0, 0. I'm going to go down to negative 3, back up to 0, up to positive 3, and then back down to 0. So my final graph, y equals negative 3 sine x, is going to look like this orange graph. So I'm going to put all these over here too. And then down to here. So graphing a y equals 3 sine x graph versus a negative 3 sine x, it's the same amplitude, same range. The only difference is instead of starting up, we start down. All right, that's y equals negative 3 sine x. The next graph I want you to try is y equals 1/2 cos x. So before we start, it's always a good idea to start with sort of like that base shape. And we won't always do this, but until you're super comfortable with these graphs, I'll just make it a bit of a darker gray. We should start by putting the base shape down. So y equals cos x graph. So again, if you think about going around your unit circle, it follows x. So we've got our points. Oh, sorry, that's +1. +1, -1, 0, and 0, -1. So if we're now going to follow x, we're going to start at 1, go to 0, go to -1, and go to 0. So first thing we're going to do is put on our base cos x graph. So we're going to start at 1, which isn't the last one, was it all the way? Yeah, I changed the scale. So this one, it's a y value of 1. And then at pi/2, you're going to go down to 0, down to -1, back up to 0, and there. So you can kind of, I'll do this one dotted. I just want to remind you what your base cos x graph looks like. I can even go to the left if I want to. Okay, so now having this base shape in mind, we want to look at this new graph. We have 1/2 cos x. I'm going to get a vertical shrink by 1/2. So what's that going to affect? Well, it's not going to affect the scale of the graph. The scale of this graph is pi/4, 4 grid lines to get to pi. The amplitude of my graph is going to be 1/2 because it's the absolute value of a. The period not affected, 2 pi, which means my key points are still going to happen every pi/2, which is still 2 grid lines on this graph. The domain is still, that came out as a straight bracket, still -infinity to infinity. And my range is going to go from -1/2 up to +1/2. Okay, so now can you sketch the y equals 1/2 cos x graph? The biggest difference is instead of starting at 1, you start at 1/2. Then you still go through 0. You go down to -1/2, back up to 0, and then up to 1/2. So that's one cycle of my cos x graph. And then to the left, same thing. Same 0, but now I only go down to 1/2. Back up to 0, and now I go up to 1/2. And that's my y equals 1/2 cos x graph. And the biggest difference here, like if you think about how like this comes from the unit circle, is that all these points, instead of being 1, 0, it would be a 1/2 0. Instead of being 0, 1, it would be 0, 1/2. And that's how you could kind of get it to go through the cycle. All right, so that is the first video. So now you're going to go to the part 1 of the worksheet, and you're going to do questions numbers 1 to 4. So these are just the questions that have a transformation of a.